Hey, welcome back to Calculus. We're going to finish up section 7.2, continuing to look at an integration techniques for powers of trig functions. But in this second part, we're going to look at powers of secant and tangent. Okay, so we're going to look at not powers of sine and cosine, but secants and tangents. So I want to tell you some techniques to handle things of the form tangent to the m times secant to the n, where again, m and n are non-negative whole numbers. Okay, so that's the goal. Just show you this technique. We'll get going here. Just like with sine and cosine, there's some kind of relevant identities. Like I said before, the most important identity in the world, or in the trigonometric world, is sine squared x plus cosine squared x equals 1, the Pythagorean identity. And I say it's the most important because lots of other ones you can derive from it. The second one that's written there, if you divide everything by cosine squared, I'm just going to kind of do it in this laser pointer here for a second. Dividing everything by cosine squared certainly also gives me an identity, but sine over cosine squared, that's tangent squared. Cosine squared over itself is 1, and 1 over cosine squared is secant squared. Okay, so dividing that thing by cosine squared gives you another identity. Tangent squared plus 1 is secant squared. And then I'm going to manipulate that. Any even power of secant, right? I can think of secant to the 2k as secant squared raised to the k. So I can write an even power of secant as a power of tangent squared plus 1. Or if I solve the equation for tangent squared, I can write an even power of tangent as tangent squared to that power. So I can write that even power of tangent as secant squared minus 1 to some power. Okay, so those are the relevant identities. You probably want to jot down, I would say, this one and this one as before we proceed along. So just like in the previous lecture, I'm going to just kind of illustrate with some examples, and then we'll summarize about what kind of strategies we have here. So here I'm looking at tangent to the 6th times secant to the 4th. So let me show you how I want to handle that integral. I'm going to take the secant to the 4th, and I'm going to split off a secant squared. Talk strategy in a minute here, but I'm just going to do that. And then when I split secant squared off of secant to the 4th, it of course leaves me another secant squared. And that other secant squared I'm going to use in terms of that identity we just wrote. So I'm going to replace the secant squared in the middle factor there with tangent squared plus 1. So I'm using that identity. Okay, so everything else besides the secant squared that I split off is in terms of tangent, and that kind of motivates the idea that I'm going to make a substitution. I'm going to let u equal tangent. Why is that a nice substitution? Because du, the derivative of tangent, you remember, is precisely secant squared. It's precisely what we split off. So the secant squared dx was very strategically set up to be my du. So when I rewrite this integral now in terms of u, I get a polynomial again. I get u to the 6th times u squared plus 1 quantity du. Multiply that out to see what powers we have to deal with. I've got u to the 8th plus u to the 6th. That's a polynomial in u. I can integrate it with the power rule. Adding 1 to the exponent, dividing by the new exponents. I've integrated, so I'll add my constant of integration. And the last thing to do is to remember, well, u is equal to tangent. So I'm going to rewrite this thing in terms of the original variable. 1/9 tangent to the 9th plus 1/7 tangent to the 7th plus my constant. Okay, I'll zoom out a little bit so we can see the whole computation in all of its glory there. So the antiderivative of tangent to the 6th times secant to the 4th, so in one form anyway, is 1/9 tangent to the 9th plus 1/7 tangent to the 7th plus a constant. Why did the technique work? I'm just summarizing about, or hinting at my strategy rather, not summarizing, hinting. This technique worked because I had a power on secant that was, first of all, big enough and even so that when I pulled off a secant squared, what remained could be written in terms of tangent. So letting u equal to tangent turned that into a polynomial in u. Okay, that's the executive summary. Let's look at another one. The previous method I just did isn't going to work because if I pull off, without, I shouldn't say that so uniformly, but it's not going to work without a modification. Because if I pull off a secant squared here, well, 7 minus 2 is 5, yeah? And 5 is odd. So I'm not going to be able to write 5 as a power of secant squared. So that tangent identity isn't going to work for me, yeah? But I could do the following. I'll summarize it towards the end. So I'm going to, instead of splitting off a secant squared, I'm going to split off 1 power of secant and 1 power of tangent. So I'll lower the tangent by 1. I'll lower the secant by 1. And then I'm going to split off, and I'm going to write them in this order just because I'm used to it. Secant times tangent. Okay, so you can stop the video and just make sure that if you multiplied that back out, you'd get the original expression. And why am I doing that? Let me hint at my strategy this time beforehand. Secant times tangent is the derivative of secant. So if I were able to let u equal secant, then things are looking pretty good here. But this thing needs to get replaced in terms of secant. Well, good news. I have an even power of tangent. Our identities, you can stop the video and look back. We can write even powers of tangent in terms of secant. Let me do the details. So I'm going to write this as tangent squared squared okay, why would I do that? Because tangent squared is secant squared minus 1. Secant squared minus 1 quantity squared. Still got this secant to the 6th. Still got my secant times my tangent. But now that I've written it in that form, I've sort of revealed what my idea is. I'm going to let u equal the secant. Why do that? Because then du is precisely secant tangent. Okay, so this secant tangent dx that we split off there, it's perfect to be du. So if we make the substitution, I'm going to pull off to the left here so I have room. I've got u squared minus 1 quantity squared times u to the 6th du. Polynomial in u. Okay, so we're not done, but we have to integrate that. So that's what these techniques do. We're making kind of a judicious substitution to turn our trig integral into a polynomial integral in the new variable. For this particular one, I would have to multiply out u squared minus 1. Trying to put in lots of details for you here, then distribute that u to the 6th. Rules of exponents everywhere. Integrate it using the power rule. Add the constant when you've taken an antiderivative. Last thing you need to do, replace u with secant. Okay, so I've got 1/11 secant to the 11 of x minus 2/9 secant to the 9th power of x plus 1/7 secant to the 7th power of x plus a constant. Zooming out a little bit to look at our computation in all of its glory. Notice how many lines I wrote. I'm always willing to do that in the name of accuracy. And again, how did it work? Both exponents were odd, which gave me enough room to split off a secant tangent. And since they were both odd, the remaining exponent on tangent was even, so I could replace that with some power of secant squared minus 1. And then the substitution u equals secant is going to work like a charm. Okay? So good. We sort of know what to do if the exponent on secant is even. We know what to do if they're both odd. Let's summarize that. So just real quick summary, you're looking at an integral tangent to the m, secant to the n. Well, if n is even, and at least 2, so there's at least 2 powers of secant there, I'm using this kind of informal terminology. Split off a secant squared and let u equal tangent. Okay, du is secant squared dx. That was like the first example. Or maybe both m and n are odd. If that's the case, split off a secant tangent and let u equal secant. Splitting off one power from your odd tangent will leave an even number. You can rewrite everything in terms of secant, let u equal secant. It's like the second example. So the other cases, I don't mean to make them so frowny face, but they're not as nice to me as the first two cases. Well, it's when what we said above isn't true. So maybe when n is odd and m is even. Yeah, we'll have to worry about that case. Or if there are no secants whatsoever, right? If n is 0, then the secant term isn't even there, and it won't really matter what m is. Oops. Or if there's no tangents at all. So there's so it's just powers of secant, then it doesn't really matter what n is. Right? So we have to kind of treat these cases separately. We won't worry about all possible examples here. You just kind of take them as you go. I'm going to state this. You want to jot these down. Come to an office hour or write me an email or something like that. We can make an appointment if you want me. But from Math 109, both of these integrals are done with elementary substitutions, U substitutions. So I'm just going to kind of throw them in here that the integral of tangent is the natural log of the absolute value of secant, and the integral of secant is the natural log of secant plus tangent. Okay, so those are formulas from Math 109, for example. Calc 1. You do them with U substitutions. And why I mention them here, I'm using, you'll have to scroll back if you don't have the parameters down, but tangent x, well, that's when m is 1 and n is 0. Yeah, this is when m is 0 and n is 1, the secant one. So those are special cases. All right. So let me show you how you handle some tangents where the powers are bigger than 1, like tangent squared. Right? With tangent squared, I'm going to handle it with a trig identity. The Pythagorean identity from the top of the lecture here says that tangent squared is equivalent to secant squared minus 1. Right? And I know an antiderivative for secant squared, it's tangent. Antiderivative for 1 is x. So that's how you integrate tangent squared. Then other powers of tangent you kind of treat similarly. Here, let me show you the cube. I would rewrite this thing as, well, tangent times tangent squared is one thing I could do. And then replace tangent squared with secant squared minus 1. All right, distribute that through and distribute the integral through 2. I'm going to do it on one line because I'm going to run out of room. I'd have the integral of tangent times secant squared minus the integral of tangent. All right, well, this first one we can do with an elementary substitution, right? If we let u equal tangent, du is secant squared. So this first integral just has the form u du. The second integral is the one we just did above. That's the natural log of the secant of x. Right? The antiderivative of u is 1/2 u squared, and since I'm out of room here, I'm going to substitute back all on one line. So I'm not asking you to memorize all these integrals. I'm trying to give you the idea of how to handle them. If you want to take a Tyler Evans challenge, I just did tangent squared and tangent cubed. Try tangent to the 4th. See if you can't modify my method and do tangent to the 4th or tangent to the 5th. You'll catch on to the pattern. All right. For powers of secant, it's a reduction formula. We're going to use a reduction formula to do powers of secant. Yeah, I like to put reduction formulas in nice purple boxes. So here, let me put a nice purple box. This reduction formula was first mentioned back in the integration by parts formula, but it tells me that I can integrate a power of secant by writing down some expression that involves secant and tangent, plus an integral that involves the power of secant, and that's a typo in my lecture. Sorry about that. This should be n minus 2. It reduces that power on secant by 2. Okay? So how do you deal with something like this? Notice that the first case that I wish was true isn't. That's not an even number. That's what I'm really hoping when you give me one of these. So if that's not an even number, then I hope the other one is odd too. It's not. So this is an unhappy case. M is even, but N is odd. So basically what I do in this case is take your even term and rewrite that power of tangent as secants. So let me try to leave that reduction formula visible as long as possible here. So I'm going to replace my tangent squared with secant squared minus 1. Okay, then I need to distribute that. So I've got the integral of secant to the 5th minus the integral of secant cubed. And then I would apply the reduction formula. I'm going to have to zoom out a little bit if you want to keep it visible while I'm writing. So in particular, I would split this integral. Think of this secant to the 5th dx, subtract the integral of secant cubed dx, and then use the reduction formula on the secant to the 5th. Right, so I'm referring to the purple box above when I write down that integral of secant to the 5th, n is 5, right? So it's 1 over 5 minus 1, secant cubed, tangent, plus n minus 2 is 3, n minus 1 is 4, so plus 3/4 of the integral of secant, lower that 5 by 2. This minus secant cubed dx has to come along for the ride. And now I'm going to zoom out and scroll. We don't have the need for the reduction formula anymore, at least right now. And then just like before, I'm going to gather like terms. So I've got 1/4 secant cubed times tangent. 3/4 of that integral minus one of those integrals, well, that's minus 1/4 of them. So that's where we are so far. And then I need to use that reduction formula again, right? Because I have dropped the exponent from 5 down to 3, but we have to integrate that secant cubed. Okay, so you can pause the video and go back, or maybe you wrote it down. I'm just going to try to do it from memory. So I've got 1/4 secant cubed x tangent x minus 1/4, put a bracket so I distribute things correctly. And now I'm applying that reduction formula when n is 3. So it's 1 over n minus 1 times the secant of n minus 2, so that's secant to the 1st power, times tangent, plus the coefficient is n minus 2 over n minus 1. So n here is 3, so that's 1 over 2 times the integral of secant, lower the exponent by 2 to the 1st power. Okay, so there's the application of the reduction formula. What I'm doing right now is cleaning up coefficients. Distribute that minus 1/4. So I've got minus 1/8 secant tangent minus 1/8 the integral of secant x dx. And by our special case, the integral of secant x dx, you can pause the video and go back and look at it. It's a known value. So for a second here, I just have to copy without making an error. Minus 1/8. The antiderivative of secant we wrote above is natural log of secant plus tangent in absolute value. We're done integrating, so I'm adding my constant. Okay, so I hope that that was useful for you. I just want to scroll out to look at this in all of its glory. So once again, I'm trying to convince you that instead of squeezing these computations into little bits of space, I write many lines. I'm using electronic paper, so I have an unlimited amount of it here, but on each one of those lines, I didn't do very much. So if I went to check this answer in the back of the book and it was wrong, I could start line by line, kind of checking my computation. It would be easy for me to find where, if any place, I made an error. All right, so that's powers of secant and tangent. I want to mention that there is one more topic in this section that I didn't do. I might make a separate video, I might not, I'm still thinking about it, but they're an important class of integrals, so we might come around. You might want to just read about, sorry about that, my brain's starting to melt here at the end, read about integrals of the form like sine of m times x, cosine of n times x dx. And also integrals sine, cosine of the same things. That's also in this section. I won't put any questions on your examination about it, but just for your information, it is covered in this section, and you might want to check those out. It uses some more identities. Maybe if we have time in the Zoom class meeting, we'll circle back and talk about them. Okay, thanks for listening.